Hello. Hello and welcome to this video. This is again the theory side of it. So we have seen in the last video how to insert and perform certain operations on geometric types, which we discussed in the video before that one. So we proceed in the data types chapter, that is chapter 8 of Postgres manual. And we are going to first deal with network address types, and we will see how far we can go. So I would like to justify why we are going through manual is because there can be minor details uh, in the theory side of it, which you may not get just by writing code. There might be edge cases. I'll give you an example very soon. So let's begin with network address types. So what are network address types? Those are your IP addresses, both IPv4 and IPv6, and MAC addresses. Now it is better to use these types instead of plain text type to store network addresses. Now, for example, if a database does not support network address types, I don't know whether MongoDB supports or not. So usually what people do is they put it inside string. Okay. But you should not do that if you are using PostgreSQL. The reason is these types offer input error checking and specialized operators and functions, which we will see in section 9.12. That is the next chapter, functions and operators. So there are 4 types which we have. One is CIDR, which could be 7 or 19 bytes depending on IPv4 and IPv6 networks. Then we have INET, which can be 7 or 19 bytes, which is for IPv4 and IPv6 hosts networks. Then we have MAC address, which are typically 48 bits, that is 6 bytes. And then we have MAC address 8, which is 8 bytes. Honestly, I don't know what this MAC address 8 of 8 bytes is. I have never seen MAC address other than 6 bytes. So you might want to perform a search on what is EUI64 format. Now, when you sort INET or CIDR types, IPv4 addresses will always sort before IPv6 addresses, including IPv4 addresses encapsulated or mapped to IPv6 addresses, such as : 10.2.3.4 and so on. So this is a minor detail which you might miss if you don't read the manual. So for such details, we need to read the manual. Now we will discuss INET. So INET holds the IPv6 or IPv4 host address, and optionally its subnet all in one field. The subnet is represented by the number of network address bits present in the host address, the net mask. If the net mask is 32 and the address is IPv4, then the value does not indicate a subnet, only a single host. In IPv6, the address length is 128 bits. So 128 bits specify a unique host address. Note that if you want to accept only networks, you should use the CIDR type rather than INET. The input format for this type is address/y, where address is an IPv4 or IPv6 address and y is the number of bits in the bitnet mask. If you don't understand this terminology, then you need to figure out how TCP/IP and net masks work, because discussing what is a net mask is out of scope. So I'll say, for example, this. So consider IPv6 address. It has 4 octets. Now let's say that you specify that net mask is 24 bits. Then first 24 bits are fixed and last 8 bits can vary. So you can have up to 255 or rather 256 hosts in that subnet. So that's what net mask is. If the /y portion is omitted, then net mask is taken to be 32 for IPv4 or 128 for IPv6. Now, for IPv6, the net mask will almost always be 128 because every address is unique. So the value represents just a single host. On display, the /y portion is suppressed if the net mask specifies a single host. Now we discuss CIDR types. The CIDR type holds an IPv4 or IPv6 network specification. Input and output formats follow caseless internet domain routing conventions. The format for specifying networks is address/y, where address is the network's lowest address represented as an IPv4 or IPv6 address, and y is the number of bits in net mask. If y is omitted, it is calculated using assumption from the older classical network numbering system, except it will be at least large enough to include all of the octets written in the input. It is an error to specify a netmask address that has bits set to the right of the specified netmask. So certain examples could be that this is the CIDR input 192.168.100.128/25, and the output will be same, and abbreviation will be also same. Now, if you specify 192.168/24, then last two octets become 0.0 and abbreviation is 192.168.0/24 because these three octets contain 24 bits. So you can go through these examples and try to understand those. If you don't understand this example, then I would suggest that you go and study on the networking side of operating system, Windows or Unix, both will work. Now the difference between INET and CIDR is, the essential difference between INET and CIDR data type is that INET accepts values with non-zero bits to the right of net mask, while CIDR does not. For example, 192.168.0.1/24 is a valid INET but not for CIDR. Now the tip is, if you do not like the output format for INET or CIDR value, try the functions host, text, and abbreviation. Now we will talk about the MAC address, which is the address of the network interface card, and these are usually 48 bits, okay, and they are unique also. So input is accepted in these formats, which you can see. So this is the usual way of inputting the MAC address, right? So this could be up to FF. So 255 is 1 byte. So these are 6 bytes. So 0 to FF, that is 256 numbers, and then you have got 48 bits of those. These examples all specify the same addresses. Upper and lowercase is accepted for the digits A through F. Output is always in the first of the form shown. So this is the output format, and ideally this should be your input format as well. Okay, you can use these formats, but I personally would not recommend, because that's not the standard way of writing the IP address or MAC address rather. IEEE standard 802-2001 specifies the second form, which shown with happens as the canonical form for MAC addresses, and specify the first form with colons as used with bit reversed MSB first notation, so that 08002B 010203 is equal to 10:00:D4:80:40:C0. This convention is widely ignored nowadays, and it is relevant only for obsolete network protocols such as tokening. PostgreSQL makes no provisions for bit reversal. All accepted formats use the canonical LSB order. The remaining 5 input formats are not part of any standard, so as such they should be ignored. Now we come to MAC address 8, which is the EUI64 format. I have no idea what it is. Okay, known for example from Ethernet card hardware addresses. All the MAC addresses are used for other purposes as well. This type can accept both 6 or 8 byte length MAC addresses and store them in 8 byte length format. MAC addresses given in 6-byte format will be stored in 8-byte length format with the 4th and 5th byte set to FF and FE respectively. So that's how you store 6 bytes into 8 bytes. The 4th and 5th are always FF and FE. Note that IPv6 uses a modified EUI64 format where the 7th bit should be set to 1 after the conversion from EUI48. The function MAC address 8 underscore set 7 bit is provided to make this change. Generally speaking, any input which is comprised of pair of hex digit on byte boundaries, optionally separated consistently by one of colon, hyphen, or dot, is accepted. The number of hex digits must be either 16 or 12, that is 8 bytes or 12 bytes. Leading and trailing white spaces is ignored. The following are examples of inputs that are accepted. So this is how you do it, okay? And if you see this example, so this is 08002B 010203. So 4th and 5th byte are set to FF and FE. And 7th bit is set to, what was it? Okay. 7th bit should be set to 1. So let's look at 7th bit. So this is 8, all right? So what 8 is, that 8 is basically 1000 in binary, 1000, that is your 8. And then there will be 4 zeros to the left of that because you have 8 bits in the byte. Now if you set the 7th bit from left hand side to 1, then it will become 10, which is an hexadecimal is 0A. So that was all about network types, address types, and now we will see bit string types. So bit strings are strings of ones and zeros. They can be used to store or visualize bit masks. There are two SQL bit types, bit_n and bit varying n, where n is a positive integer. Bit type data must match the length n exactly. It is an error to attempt to store shorter or longer bit strings. Bit varying data is of variable length up to a maximum length n. Longer strings will be rejected. Writing bit without a length is equivalent to bit 1, while bit varying without a length specification means unlimited length. If one explicitly casts a bit string value to bit n, it will be truncated or zero padded on the write to exactly n bits without raising an error. Similarly, if one explicitly casts a bit string value to bit varying n, it will be truncated on the write if it is more than n bits. So for example, here you can create a table test with the bit 3 and bit varying 5. So two columns A and B. Now in the A you insert 101, in the B you insert 00, then you can insert 10 for A and 101 for B. So you see what will happen is that this insertion will fail because the length is given as 3, but you are inserting a bit string of length 2. So it wouldn't match the specification of the table schema. So you can cast it to bit 3 and then it will accept it. And if you select this 10 will become 100 and this 00 will remain unaltered. So take care of that. Now, I think we have time to go through text search types. So text search types are important in the sense that it allows you to perform a full text search on the column. Okay. So for example, if you are used to using Elasticsearch, you might replace that with the full text search of PostgreSQL. But note that you will have to do a lot of work for that. Okay, it is non-trivial to just make use of full text search just like that. It is a very advanced topic. Not very, it is an advanced topic, and we will cover this almost at the end. So in any case, I will let you go through the manual or rather we will go together. I think these are 2 pages, so we can go through it fairly quickly. So let's see. PostgreSQL provides two data types that are designed to support full text search, which is the activity of searching through a collection of natural language documents to locate those that best match a query. The TS vector type represents a document in a form optimized for text search. The TS query type similarly represents a text query. So chapter 12 will have a detailed explanation for this facility, and 9.13 summarizes the function and operators. So we'll go through chapter 12 and 9.3 in order. So what a TS vector is, a value, a TS vector value is a shorted list of distinct lexemes. I hope that I pronounce that all right, which are words that have been normalized to merge different variants of the same word. Sorting and duplicate elimination are done automatically during input as shown in this example. So suppose there is a sentence like a fat cat sat on a mat and ate a fat rat, and you cast this to TS vector. So you see A has come many times, A, 1, 2, 3. But when you select, those three A's are merged and come once. Then we have and, okay? So we have 1 and then 8. 8 has come once. Now if you see, I think others are not repeated, okay? Fat is repeated, so fat also has come once. So basically, duplicates are merged here and they are sorted. Now, if you have to select something which contains white space or punctuation marks, you put them inside double quotes, okay? We use $quoted string literals in these examples, and the next one to avoid the confusion of having to double quote marks within the literals. Embedded quotes and backslashes must double. So you see here the text was quoted with double dollars. Okay. Now if you see the next example, so this is a double quote. Okay. And now yeah, this is double quote. So embedded quotes and backslashes must be double. So it's an embedded single quote, but it is doubled here. Okay. So when you select, it becomes Joe's a contain lexeme quote the. Now integer position can also be attached to lexemes. So we have 1, 2, 3, and so on. We attach integer positions here. And finally, when you select the TS vector, it will tell you all the positions of A, 1, 6, and 10, and comes at 8, and fat comes at 2 and 11, and so on. A position normally indicates the source word's location in the document. Positional information can be used for proximity ranking. Position values can range from 1 to 16,383. Larger numbers are silently set to 16,383. Duplicate positions for the same lexeme are discarded. Lexemes that have positions can further be labeled with a weight, which can be A, B, C, or D. D is the default and hence is not shown on output. So you can associate a weight, for example, A here, B here, and then C, and then we have D for this. So those weights will also appear in output. Weights are typically used to reflect document structure, for example, by marking title words differently from body words. Text search ranking functions can assign different priorities to different weight markers. It is important to understand that the TS vector type itself does not perform any word normalization. It assumes the words it is given are normalized appropriately for the application. For example, the fat rats. The fat rats. So if you select this, you get fat rats in the. Okay. For most English text searching applications, the above word would be considered non-normalized, but TX vector doesn't care. Raw document text should be usually be passed through to TS vector to normalize the words appropriately for searching. So if you apply the two vector function with, you have to also supply the language name, that is English, the fat rats. Then you see what it does is it discards the word the. Okay. It discards because it's a common word. So in general, when you search for a string, certain words have or no meaning. For example, a, and, the, for, these are ignored, off. Now let's come to TS query. So a TS query stores lexemes that are to be searched for and can combine them using the Boolean operators and, or, and not, as well as the phrase search operator followed by. There is also a variant of the followed by operator where n is an integer constant that specifies the distance between the two lexemes being searched for is equivalent to 1. Okay, the default followed by is 1. Parentheses can be used to enforce grouping of these operators. In the absence of parentheses, not binds most tightly, followed by next most tightly, then and with or binding the least tightly. So for example, we have, say, a string fat and rat. So this is the operator which we have, and we select that as TS query. So TS query shows here. Then you have got fat and rat or cat. We got another TS query. Then we have fat and rat and not cat. So here not and operators are here. Now it may not make sense unless we see a practical full text search example that how it works. But reaching there will take time. We just can't approach full text search without going through the theory. And to actually perform the full text search, what we need to do is we need to read chapter 12 and we need to read section 9.13. Without reading those two, we can't approach the full text search. So this particular section, when I'm talking about these operators, it does not immediately make sense that what is the use of this. Optionally, lexemes in a TS query can be labeled with one or more weight letters, which restricts them to match only TS vector lexemes with one of those weights. So for example, fat is being labeled AB and we have cat, so the weights also come in the picture. Also, lexemes in a TS query can be labeled with star to specify prefix matching. For example, super colon star. So it can match any word which begins with super. Okay, for example, Superman. The query will match any word in a TS vector that begins with super. Quoting rules for lexemes are the same as described previously for lexemes in TS vector, and as with TS vector, any required normalization of words must be done before converting the TS query type. The toTS query function is convenient for performing such normalization. So like toTS vector, you have toTS query to normalize the search query. Note that toTS query will process prefixes in the same way as other words, which means this comparison returns true. So for example, you have a TS vector here, postgraduate. We normalize this using toTS vector. And then we have a TS query, okay, which starts with Postgres, okay. Now we do a prefix match on this and then we find that it is true. So similarly, what happens is here, because Postgres that stems to PostGR, okay. So up to PostGR it matches and then that is good enough match. Then we have postgraduate and we have Postgres. So if you see this select operation here, so it gives you the TS vector and gives you the TS query. So you see what is used to match this. So here if you see carefully, then the TS vector suppresses ATE and also suppresses ES. So that is something how search engines work. I don't know. I'm not a search engine specialist. So I will stop here. We covered quite a bit of stuff, and in the next video we'll go back to our employer stuff and we'll do regular SQL practice. Okay, we will continue theory. So at this moment the theory and practical will diverge. Okay, so we will continue with the tables of employee which we had created earlier. This is a new machine, so I don't know if I have the table description, but I'll manage. Okay. And we will continue the practical in the next video of Postgres. database. So with this, I will come to the end of this video, and I hope that you are enjoying and finding it informative. So thanks for watching the video, and I'll see you in the next video. Enjoy.